Hello, everyone, and welcome to this episode of One Man and His Whiteboard. We're going to talk about today decimal, binary, and hexadecimal. To have an understanding of number systems, it's convenient to understand why it is that we use numbers the way we do. In the everyday number system we use in the world to calculate money, well, unless of course you live in England, then we have a very complex way of calculating measurements as compared to meters, kilometers, centimeters, and so on. We still have inches and feet and things. So decimal-based everything is quite easy to use, quite convenient to use. I know that in the UK we are converting over to the metric system, which of course is based on multiples of 10. In the United States, we still have our feet and inches and gallons and things, which is based on a different system completely. But I'm ranting now, so let me get back to the simplicity of decimal. It's based on a function of factors of 10, and any number system analysis will teach you that you have relevant functions, relevant numbers in positions that can be used to base a number system on. I'll choose 8 because, as you'll soon see, it effectively ends up becoming about binary, this entire section anyway. In the decimal world, our number system is based on 10. And quite often when people are asked what numbers are they based on, they say 1 to 10, which of course is incorrect. Our number system is based on 0 to 9. Because 10, as you'll see in a minute, is actually not a number from the number series. It is a calculated number based on many positions. So in this one, what am I talking about? You may be thinking to yourself, what is this guy talking about? What I mean is, what number or what range of numbers can you put in this field? Well, you can only put 0 to 9. 10 is actually a combination of 2 number positions. 1 from this position and 0 from this position. Now, I did this in this convoluted way because I'm hoping that you've suddenly gone, and light bulbs have gone off all over our audience. And let me see if I can I draw an adequate light bulb? I hope so. So light bulbs have gone off and you suddenly realize that 10 is not a single number such as 0 to 9 are. 10 is a multi-component number made of 0 units and 1 from this column. Now, when I was in school, which was a while back, we called these tens and we called these units. We called these, of course, hundreds. So if I had 101, that would be 100, 0 tens, and 1 unit. So I have 100 oranges and 1 orange. If I had $323, I had $300, 2 $10, and 3 unit. Now I may have 323 $1 bills, or I may have 3 $100 bill, 2 $10 bills, and 3 $1 bills. So it's very important we understand how we build this mathematical system. So let me delete some of these and get them out the way so we can look at this in a little bit more detail. Basically, this entire system is based on the premise that you raise the first column to the power of 0, second column to the power of 1, the next column to the power of 2, and so on. So if we are doing base 10, x represents 10. Now, I don't want to go off on a mathematical tangent here. Anybody get the geometric joke there? I apologize. I don't want to go off on a mathematical tangent, but anything, and I don't want to explain why, anything raised to the power of 0 is just simply 1. Okay? It's just 1. It is. So that's units. X to the power of 1, well, that x being 10 is 10. So now you understand where the 10s come from. X to the power of 2 is 10 times 10, so it becomes 100. X to the power of 3 is 10 times 10 times 10, and it becomes 1,000. And you can see how we go on from here. So we can use any number from 0 to 9 to represent in this position. So if we write down 323, we have 3 100s, 2 10s, and 3 1s. 300s, 2 10s, and 3 1s. Now, a little story for you, bit of history. Way back in the day, when they first started numbering the years, the monks and the mathematicians of the time, the learned of the time, did not understand the concept of 0. So the very first year they calculated was year 1. Of course, we know now that at the end of the first year, it becomes 1. So that should have been called year 0. And they realized this problem, that they'd numbered it wrong quite a while later, I believe several hundred years later, maybe even 1,000 years or so later. And they decided to adjust it. They decided to adjust the year to pay back the year that they'd missed. Well, this caused a lot of problems with the people of the time, because they actually thought that their masters were taking away 1 year of their life. So there you go. So it's best to get it right first time, eh? So understanding the mathematics that we have here, we have x to the 0, x to the 1, x to the 2, and x to the 3. Let's take this to another sheet, and let's change colors. I'll go for a darker blue this time. And let's talk about how we could extend that using a different base number system. So let's write our x's down again. Let's just make 8 of them. It's very convenient to have 8 of them for binary. And the whole purpose of this, of course, is for binary. You don't need decimal mathematics. We kind of teach that in school. I remember when I was in school, they always made us calculate up to 12 times tables they made us do. And it was very easy to do 12 times tables. I just realized I did 9. There you go, my bad. 1, 2, 3, 4, 5, 6, 7, 8. So probably because back in the day there were 12 pennies to a shilling, which is why we did it. It's a shame that they never taught us up to 16, because that would have become very useful for the next section we're going to talk about. We talk about hexadecimal, but leave that for now. Let's just go back to number systems here. So remember that the first column is raised to the power of 0, then 1, then 2, then 3, then 4, then 5, then 6, then 7. So if we base this around the number 2, so we say we have base 2. Remember now, back here we had base, I didn't actually write it in, this is base 10. So here now, we're going to have base 2. Remember what I said at the start, the one rule, you just have to accept this. If you want to go off and research why this is the case, I encourage you to Google this and look at it on the internet. But anything raised to the power of 0 is 1. So then 2 to the power of 1 is 2 times, well, not times anything. So that's just simply 2. This will become 2 times 2. This will become 2 times 2 times 2, and so on. And I'm going to write these out in full because it's very important we memorize these when we do our binary mathematics. So, if you've ever gone to college, the first class you do is 101. So 101, remember, 101, we talked about this earlier, is 100, 0 tens, 1 unit, 101. So 101 now in the binary model, 101, it is 1 4, no 2s, 1 1. So that represents 5. What if we want to calculate 3, 2, 3? Well, hold on, stop. That's not allowed. You can't have 3, 2, 3 in binary because just like 10, base 10 allows numbers from 0 up to 1 minus the base, 0 to 9. Binary allows from 0 up to 1 minus the base. So you can have from 0 to 1. So effectively, you can have 0 or 1. Those are the only two numbers that are allowed here. So I want to draw a little line across here, separating this so we all understand that the rules are above and the calculations are below. So I can do numbers, but I can only do 0 or 1. So can I have 1, 1, 1, 1, 1, 1, 1, 1? Sure. What does that add up to? Well, that's 128 plus 164 plus 132. Oh, okay, this is getting hard now. Let me show you a little shortcut. Shortcuts are always great. What if I have 1, 1, 1? I have 1, 4, 1, 2, and 1, 1. That adds up to be 7. Now, pay attention to this. If all of these are 1, okay, it's 1 minus the next column. So this is 8. If these are all 1, it's 1 minus the next column. It's 7, which is 8 minus 1. So how does this work with mathematics? Let's just take a time out, and I like to revert back to decimal mathematics here because it really helps people. If I add 1 to this, it becomes 324. All right, what if I get to 9, 9, 9? If I add 1 to this, we're taught in school that becomes a 0 and you carry the 1. That becomes a 0 and you carry the 1. That becomes a 0 and you carry the 1. So 999 plus 1 is 1000 minus 1. So if you max out the possible number in every column, it's going to be the next column minus 1. Now, this doesn't really matter in decimal because we're so used to it. In binary, this can be very, very useful. Because what if I say to you, calculate what is 1, 1, 1, 1, 1, 1, 1? 7 ones. So I know it's 127. Because it's 128 minus 1. Because if I add 1 to it, 0, carry the 1, 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 1. Just simply adding 1 to that number becomes 128 with nothing else. And little shortcuts like this help you with binary. And binary becomes very important in the networking world and in the computer world because we have to do things in the networking world with subnets. We have to do things in the computing world with numbers, maybe doing some kind of programming, assembly language programming. Okay. So it's all based around 8 or multiples of 8 because it's a multiple of 2, which basically is based on the binary value of 0 or 1. And the reason behind this, of course, if you want to study computer history, is because 0 and 1 is a simple system where something can be off or on. And once you build something on, something off or on, and have rules of how to change the off and the on, you've suddenly built a calculator. And it's easier to calculate a number into binary, let a computer do the mathematics on it, then convert it back to decimal than it is to do the calculation in decimal in our heads on a piece of paper. Because computers are very fast. So we know that in binary, we have zeros or ones. We know that we have the base to the power of starting off 0 and going away to 7. And now we understand that we multiply these out based on 2 to the power of 0, then 2 to the power of 1, 2 to the power of 2, and so on, and we end up with these numbers. And so here we are now, and we understand how to calculate numbers based on the theory in decimal, and we understand how to calculate the numbers in binary based on the theory as well. Now, before I show you one more thing called hexadecimal, I want to show you a little trick. If ever you want to write down a binary series, you probably start off like this. Okay, there's 0, then there's 1, then there's 1, 0, then there's 1, 1, then there's 1, 0, 1, then there's 1, 1, 1, then there's 1, and you get lost because you made a mistake. Now, you probably won't make a mistake with 3 bits, but by the time you get to like 5, 6, or 7, you're going to make a boo-boo. So let me show you a little shortcut, a perfect way to write in binary that never fails. Start off on the right-hand side, and you write down 0 and 1. And then you continue to repeat 0 and 1. Every 1 you alternate. Then I want you to write down 2 zeros. Then I want you to write down 2 ones. Then I want you to write down 4 zeros. Almost looks like a 6, that one. As you can see, to work with computers and networks, you haven't got to be a great artist. And I suppose if I was a great artist, I'd be selling my pictures on the internet, not putting binary things on the internet, right? So every 4, repeat. Then every 8. Then anybody want to guess what the next column is? How many zeros do I put in a line? I'll give you a clue. I alternated every 1, I alternated every 2, I alternated every 4, I alternated every 8. Anybody want to make a bet that it's 16? So if I write down 16 zeros, then 16 ones, what you'll see is I have a perfect count from 0 to 12. I have a perfect count in binary. Now, if I were to just extend this for 4 more, just so we can get to 16, because 16, of course, is a special number to us in computers. So I alternate every 1, I alternate every 2, I alternate every 4, and I continue my alternation of every 8. What you'll see, and I did say I'm going to go to 16, the sharp ones amongst you would have actually said, actually, Phil, you're going to 15. So I'm putting a range of 16. I fell into my own trap, right? I'm actually going from 0 to 15. Now, I did that on purpose to let you spot it. Maybe. Let's just move swiftly on. Yeah, so I fell into my own trap. I said, of course, let's count to 16. What I should have said is let's count to 16 rows, which is actually from 0 to 15. Okay, and that's a really important part, because adding 1 to this next column, you repeat. What did we say? You alternate these every 1. You alternate these every 2. You alternate these every 4. You alternate these every 8. You alternate these every 16. So 16 is actually 1, 0, 0, 0, 0. And for my shortcut earlier, I showed you if every field is at the maximum value, it's 1 minus the next column, which of course is, with the next column is 16. So this number is actually 15. Okay? So with that information in our heads, let's now move on to talk about hexadecimal. I'm going to use a slightly lighter shade of blue here. Let's make our same set of rules. Whoops. Remember, to the 0, to the 1, to the 2, to the 3. I encourage you, if you want to re-watch this video, I encourage you to do this with me. Watch the video by all means, then do it with me. I'm a little bit of a perfectionist, and I don't like my the X I put at the start there. I think my battery may be running out on my my mouse here. Wireless mouse, of course. All right. So following the rules we've talked about so far, we had base 10 and we had base 2. Hexadecimal is base 16. So now we want to have numbers. With base 10, it was from 0 to 1 minus the base. With base 2, it was from 0 to 1 minus the base. So base 10, it's 0 to 9. Base 2, it's 0 to 1. Hexadecimal base 16 is going to be 0 to 15. So we want to have numbers from 0 to 15. So I'm going to end up with a number of 11, 0, 9, 13, 1. So basically what we're talking about, whoops, let me just move these down 1. This is going to be, remember, anything to 1 is base, anything to base 0 is 1. And then the base 1 is the base itself. And 16 times 16. Okay, and so on. So now we've got to stop and look at this, because we've got 11 from this column, 0 from this column, 9 from this column, 13 from this column, and 1 from this column. That's 4,096, if I remember correctly. And that's 65,536. I'm now going to stop myself, and I'm of course going to load up the calculator. Why do the maths when we have a calculator? Okay, 16 times 16 times 16 times 16, 65,536. All of you out there that are going, wow, this is not my first rodeo, right? I've done it before. So that's basically 64 times 1,024. And you'll get to remember them. I've got to be honest, that was more luck than skill. But I will take the credit. I will take the praise. Please just send me an email. Yeah. So you tend to remember this. Okay. So we've got 11 65,536s, and 13. Well, if I write this down as 11, 0, 9, 13, 1, How do we know that that's 11, 0, 9, 13, 1 and not 1,109,131? So now we have a problem. How do we represent numbers bigger than 9? So what the scientific community did here, they said, well, let's just use letters. So we will use 0 to 9. And once we get past that, we'll use A, B, C, D, E, and F. So these represent 0 to 9. A represents a decimal value of 10. B is 11. C is 12. D is 13. E is 14. And F is 1 minus the base, which of course is 15. So we would now swap this out, and we would actually write in here B, 0, 9, D, 1. So we would now write in hexadecimal B09D1, which allows us to calculate what the value would be in hexadecimal. So if we have 101 in hexadecimal, that's going to be 1 256, 0 16s 1 1. That represents just simply 257. I'm going to move these up a little bit, just to maximize my real estate here. If we have 323, we'll have 3 256s, 256, 512, 768. So 768 plus 2 16s plus 32 plus 3. Okay, that's going to be 803 if I'm not mistaken. Let me just check my maths. 768. Yes, 803. So 3 256s, 2 16s, 3 units. And that's basically the essence of hexadecimal mathematics. Hexadecimal mathematics is used quite a lot in the industry. It's used for MAC addresses. It's used a lot in IP version 6 addressing. So in networking, you'll see hexadecimal very, very frequently. Now there is one more shortcut I want to show you, and that is the interoperability of hexadecimal and binary. So let's say you have a hexadecimal number that is 2, 4. From hexadecimal calculations and mathematics, we have the number 2, 4. Two 16s plus 4, we know that's 36. Okay, that's 36. So we could convert this to binary. What's 2 in binary? 0, 0, 1, 0. What's 4 in binary? 0, 1, 0, 0. So if we now add this up, 1, 2, 4, 1, 4, 0. So 0, 1, 4, 8. So just writing the binary numbers in here. The binary numbers that we saw earlier. That'll be 16. I'm going to offset them to make them more visible. for the numbers to all merge into one. So 132 plus 4, 36. So you can interchange 8-byte numbers into hexadecimal by splitting them in half. Now, you have to remember the people who did the science on this had a sense of humor. So 8 bits is known as a byte. So 4 bits is half a byte. So obviously it's going to be called a nibble, right? And this is real. I'm not making this stuff up. Remember, they had a sense of humor. So 4 bits is called a nibble, half a byte. If any non-English speakers or non-English native speakers, a nibble in English means it's a small bite. So if you take a large bite out of an apple, if you nibbled at the apple, you take small bites. It's like I said, they had a sense of humor. Okay. Well, the relationship is quite clever because you can do it the other way as well. So how do I convert from decimal to binary? I've shown you how to convert from binary to decimal. What if I want to convert, say, let's pick a number, 53. How do I convert 53 into binary? So you go along from the right until you come to the next number that's smaller than the number. So here you can see 32 is smaller than 53, 64 is larger. So, I want 132, please. I'll have 132. I want 0 128s. I want 0 64s. I want 132. Now, when you subtract 32 from 53, okay, subtract 32, that becomes 21. Okay, so we have 21 left. So 16 is smaller than 21, so we'll have one of those, please. So now you subtract 16, and that becomes 5. Now, 8 is bigger than 5, so we don't want any of them. 4 is smaller than 5, so we'll have one of them. Now you subtract 4, you end up with 1. 2 is bigger than 1, so we don't want any of them. 1 is 1, so we'll have one of them at the end, please. So 0, 0, 1, 1, 0, 1, 0, 1 is 53. So that's 132 plus 16 is 48, plus 4 is 52, plus 1 is 53. Well, the beauty of this is knowing what you now know, 0, 0, 1, 1, 0, 1, 0, 1. And by the way, you've got to sing binary, right? What did we say? 0, 0, 1, 1, 0, 1, 0, 1. If you divide that into 2 nibbles, okay, and you start off here with 0, 1, 2, 4, and then because you split it into 2 nibbles, again you start 0, 1, 2, 4. Okay, convert this into a hexadecimal value. Sorry guys, I've done to the power of. That of course is, I wrote this down to the power of. So you've got to shift these over by 1 and make that an 8. Sorry guys and gals, got a bit carried away with myself then. So what I wrote down was 0, 1, 2, 4, which is the base to the power of. I should have written down the binary, the decimal values of 1, 2, 4, 8 that maps the 4 bits, the nibble. So I want 1, 2, and 1, 1, that is 3. And I want 1, 4, and 1, 1, that is 5. So 53 is 35. Now, how do we show what we're doing? Any number written down with nothing defaults to being a decimal number. Sometimes we write down 0x at the start, or we may write down, you may see 35H, 35 hex written down. So 00110101, you may see a 0B at the start for binary, or you may just see a B at the end to show that it's binary, a lowercase b. So 53 is 35. Huh, go figure. Let's check it out. 35 in hexadecimal will be, in hexadecimal calculations, 35, there's the 16 to the power of 0, there's 16 to the power of 1, 3 16s plus 5, 3 16s are 48, plus 5, 53. So one of the beauty of working and understanding binary and hexadecimal is it's very easy to convert from decimal into binary and then just simply using from 0 to 15 as a calculation to calculate down what is hexadecimal. But of course, the other way of doing this as well is if you had 53, you divide it by 53 is, if you look at 53, you got ones, you've got 16s, you've got, what's the next one? Well, let's go back to our chart. 53 is less than 256, so you've got to make it 16. So you divide 53 by multiples of 16 and you come up with 48, which of course is 3 16s. So how many 16s form a number that's lower than 53? 3. So you get a multiple of 16, 48. How'd you get to that? Well, that's 3. So converting from decimal into hexadecimal, you take the number, decimal number you're trying to use. I'm going to draw a little dividing line down here so we don't get confused. 256 is way too much, so we want none of them, and we want no more to the left. So 16 is less than 53. You multiply 16 by 1, no, by 2, no, by 3, no, by 4. Oh, 4 16s are bigger than 53. So you write down 3. 3 16s are 48. 4 16s are 64. So 53 lies between 48 and 64. Well, that's 3 16s. That's 4 16s. So you take the lower number and you write 3 down there. Then you subtract 48 from 53, that leaves 5. And because this is the unit column, you put a 5 in there. So converting from decimal to hexadecimal, you can do it this way. You can do it with the binary level. But of course, you can do it with a calculator. I would recommend you practice doing it manually, but test it and check it with a calculator. And almost all calculators come with a scientific method or scientific function. And I can't remember. There you go. If I make it a programmer calculator, you'll see that if you have an Apple Mac, you can configure many program functions. Well, first of all, it's on base 10. You can convert that to hexadecimal, and you see you have the 0x there. Or you can choose to hide the binary, or it shows the binary by default. Okay, and you saw the use of the 0x to imply that it's hexadecimal. 0x 1000. Well, I almost said 0x 1000. 0x 10,000. You should never use that terminology. 0x 10000. Be careful about using the word 0x10,000. I was wrong on two levels there. First of all, it's not 1,000, and you should. I'm glad that I made that boo-boo. You should never do that. If you start thinking that in your head, you start building relationships between hexadecimal and decimal numbers that you shouldn't. So be warned, don't think of that as 0x10,000. Refer to it as 0x10000 or some similar naming nomenclature. Okay, be very careful using 0x10,000 because suddenly you're reverting back into decimal mode, and that's a bad thing to do. In the same way, you shouldn't regard 5 as 101. You wouldn't say 101, you'd say 0101 in binary. So the same rule goes. Should you have 54? Well, actually, let's just go with our old friend 53. Okay, be very careful saying 35 hex. What would you say if I gave you 67 in decimal? $43 hex. Sounds easy, right? Okay. What if I went to 62 decimal? Would you say 30E? No. Would you say E100 and BT9? No. So by the same rule, you say 0x3E. It's very, very, very important that you also start saying 0x40. Okay? Because as human beings, we automatically say 0x40. I've been looking at this number for 50 or more years, and I see 40. I've trained myself now to see 0x40. I know it's not 40. I've got to stop and do a quick calculation in my head to realize it's 64. But just saying 0x40 can cause a problem when you start to learn hexadecimal. Okay. So we learned about binary. We learned about decimal. Started off with decimal. We talked about binary. So a quick way to write down binary. And then we talked about hexadecimal, which is a simple way to write down numbers that can be easily understood by computers. And we understood that 8 bits can be written down as 2 blocks of 4 bits. And I showed you the relationship between the hexadecimal numbers in a single 2-digit hex number can be broken down into 2 nibbles or 2 halves of a byte. Okay, that's it. I hope you have fun practicing with your decimal, binary, and hexadecimal mathematics, and we'll see you next time.